that is given by Sandor, is correct?
Yeah.
And the title of the contribution is Flow Simulation Around Multi-Wind Turbines Using...
Welcome everyone, my name is Gabor Sandor and I'm going to talk about the flow simulation around multi-wind turbines using in cities. I'm a BSc student and I'm doing this project with Dr. Mona Ildikó and Dr. Ferenc Lipka. Our aim is to place micro-wind turbine in urban circumstances, and here are some examples for existing farms. The first tool is a Savonius type wind turbines placed on a Oklahoma Medical Research Foundation. The second is the same type but in a special configuration, so-called wind tree. The next tool is a three-blade horizontal axis turbines placed on the top of a building in one row. The next is a similar type but on a Bahrain World Center. And the last two concepts, first is a so-called wind pole and the last is a so-called aero cube. We chose the three-blade horizontal type wind turbine because this is the most common type in Hungary outside of residential area. And there are many theoretical approaches how to determine the acceptable performance of the wind turbine, and we chose the Betz-type equation because this equation does not deal with the flow around the turbines, around the blade of the turbines, except the acceptable performance. And our idea is, as I mentioned, to place micro-wind turbines on the top of the building, similar like in this picture, but in our case it would be in two rows, and the second row would be shifted by one radius in horizontal direction, and thus taking the advantage the downbeat coming from the first row to the second row. And this configuration is based on a previous research which was about investigated on the influences of two turbines on each other. So at the very beginning we created a very simplified urban environment which consists of two buildings 50 meters apart, and one is 20 meters high and the second is 60 meters. And as the first part of the simulation, the CFD simulation, is the meshing, which can be seen on the right picture. We created with the tetrahedron elements, and we also provided the inflation around the two buildings, which increased the preciseness of the calculation. We provided constant input velocity from the left side because we expect the wind would come in one direction because of the placement of the building, because these buildings would be placed, for example, at the end of a street, at the middle of the T-junction. Based on the results, we can see the nature of the flow is greatly influenced by the separation of the boundary layer, which can be due to the increased pressure against the solid wall. And above the building there is a separation bubble, and above the separation bubble there is a speeds-up zone indicated in red. And if you would place the micro-wind turbines in that area, the wind would reach the blades at a higher speed. And based on the results, we want to move that speeds-up zone closer to the top of the building. So we modified the geometry by chamfering it with 45 degrees, and we also provided an input wind profile that is more realistic. And we also and we also make more precise the mesh around the building. And this chamfering for already built buildings can be made by, for example, air deflectors. So, and based on the results, it is clearly seen that this speeds up zone came closer to the building. And by placing the turbines in that zone, a shorter pole would be needed that might cause less noise to the structure of the building. And after that, we proceed to place the micro-wind turbines in the previous environment, and we also, because of the moving part of the turbines, we had to make the mesh more dense, more precise. So we created a denser mesh bubble around the turbines, and it takes a huge computational capacity because of the lots of elements, and it takes more time than we expected. As the previous presenter said, it takes months to present the results. We didn't expect that, so while we are waiting for the results, I can only say that the next part of the research would be the validation of the simulation results by wind tunnel measurements, and we want to simulate in different setups. For example, we will try to achieve the maximum output performance power by changing the rotational speed at the constant input wind, and we also would try to modify the angle of the chamfering, and we also want to measure the noise level after that. So that's my presentation. Thank you for your attention.
Thank you very much. Thank you for being very concise. So, is there any question? Yes, please.
You do overlap the turbines, and you did indicate, like this picture, here you overlap the turbines.
Yeah.
Okay. Wouldn't it be more efficient if you just move that upwards? You did indicate some work that you referenced to about the benefit. It's hard for me to see the benefit of,
Well,
I mean, if you put it just upward on this, then you take more advantage of the higher velocity there, and then...
Well, the aim of this research is to justify the theory of what you mentioned.
Oh, good luck.
And this configuration based on the previous research, it was shifted by a vertical direction, and this is the first tile move back with the horizontal direction.
Okay, thank you. Is there any other question or comment? Yes, please, Laura.
Just a basic comment. It works very well when you have a strong predominant direction of the wind, of course, this kind of configuration. Also the configuration of the row of the turbines, and also for cutting the sharp angle of the winding. Otherwise you have to do it on all the winding. It's a comment.
Okay, thank you.
Okay, thank you. Thank you again, speaker, and I think